The Oligocene is a geologic epoch of the Paleogene period and extends from about 33.9 million to 23 million years before the present. As with other older geologic periods, the rock beds that define the epoch are well identified, but the exact dates of the start and end of the epoch are slightly uncertain. The name Oligocene comes from the Greek lambda iota gamma omicron sigma and kappa alpha iota nu omicron sigma, and refers to the sparsity of extant forms of molluscs. The Oligocene is preceded by the Eocene Epoch and is followed by the Miocene Epoch. The Oligocene is the third and final epoch of the Paleogene period. The Oligocene is often considered an important time of transition, a link between the archaic world of the tropical Eocene and the more modern ecosystems of the Miocene. Major changes during the Oligocene included a global expansion of grasslands, and a regression of tropical broadleaf forests to the equatorial belt. The start of the Oligocene is marked by a notable extinction event called the Grande Coupure. It featured the replacement of European fauna with Asian fauna, except for the endemic rodent and marsupial families. By contrast, the Oligocene-Miocene boundary is not set at an easily identified worldwide event but rather at regional boundaries between the warmer late Oligocene and the relatively cooler Miocene. Subdivisions. Oligocene faunal stages from youngest to oldest are: climate. The Paleogene period general temperature decline is interrupted by an Oligocene 7 million year stepwise climate change. A deeper 8.2 degrees Celsius 400,000 year temperature depression leads to 2 degrees Celsius 7 million year stepwise climate change 33.5 Ma. The stepwise climate change began 32.5 Ma and lasted through to 25.5 Ma, as depicted in the Paleotemps chart. The Oligocene climate change was a global increase in ice volume and a 55 meters decrease in sea level with a closely related temperature depression. The 7 million year depression abruptly terminated within 1–2 million years of the Ligurita caldera eruption at 28 to 26 Ma. A deep 400,000 year glaciated Oligocene-Miocene boundary event is recorded at McMurdo Sound and King George Island. Paleogeography. During this epoch, the continents continued to drift toward their present positions. Antarctica became more isolated and finally developed an ice cap. Mountain building in western North America continued, and the Alps started to rise in Europe as the African plate continued to push north into the Eurasian plate, isolating the remnants of the Tethys Sea. A brief marine incursion marks the early Oligocene in Europe. Marine fossils from the Oligocene are rare in North America. There appears to have been a land bridge in the early Oligocene between North America and Europe, since the faunas of the two regions are very similar. Sometime during the Oligocene, South America was finally detached from Antarctica and drifted north towards North America. It also allowed the Antarctic circumpolar current to flow, rapidly cooling the Antarctic continent. Flora and angiosperms continued their expansion throughout the world as tropical and subtropical forests were replaced by temperate deciduous forests. Open plains and deserts became more common and grasses expanded from the waterbank habitat in the Eocene, moving out into open tracts. However, even at the end of the period, grass was not quite common enough for modern savannas. In North America, subtropical species dominated with cashews and lychee trees present, and temperate trees such as roses, beeches, and pines were common. The legumes spread, while sedges, rushes, and ferns continued their ascent. Fauna, even more open landscapes allowed animals to grow to larger sizes than they had earlier in the Paleocene Epoch 30 million years earlier. Marine faunas became fairly modern, as did terrestrial vertebrate fauna on the northern continents. This was probably more as a result of older forms dying out than as a result of more modern forms evolving. Many groups, such as equids, entelodonts, rhinos, marichaerodonts, and camelids, became more able to run during this time, adapting to the plains that were spreading as the Eocene rainforests receded. The first felid, Proilurus, originated in Asia during the late Oligocene and spread to Europe. South America was isolated from the other continents and evolved a quite distinct fauna during the Oligocene. The South American continent became home to strange animals such as pyrithers and astropods, as well as litopterns and notungulates, sebecasuchians, terrorbirds, and carnivorous metatheres, like the boar hyenids, remained the dominant predators. Brontotheres died out in the earliest Oligocene, and creodonts died out outside Africa and the Middle East at the end of the period. Multituberculates, an ancient lineage of primitive mammals that originated back in the Jurassic, also became extinct in the Oligocene. Aside from the Gondwanatheres, the Oligocene was home to a wide variety of strange mammals. A good example of this would be the White River fauna of central North America, which were formerly a semi-arid prairie home to many different types of endemic mammals, including entelodonts like Archaeotherium, camelids, running rhinoceratoids, three-toed equids, nimravids, protoceratids, and early canids like Aspersion. Marichaerodonts, an endemic American group, were very diverse during this time. In Asia during the Oligocene, a group of running rhinoceratoids gave rise to the indricodes, like Paraceratherium, which were the largest land mammals ever to walk the earth. The marine animals of Oligocene oceans resembled today's fauna, such as the bivalves. Calcareous cirratulids appeared in the Oligocene. The fossil record of marine mammals is a little spotty during this time, and not as well known as the Eocene or Miocene, but some fossils have been found. The baleen whales and toothed whales had just appeared, and their ancestors, the Archaeocetaceans, began to decrease in diversity due to the lack of echolocation, which was very useful as the water became colder and cloudier. Other factors to the decline could include climate changes and competition with today's modern cetaceans and the Carcharodonid sharks, which also appeared in this epoch. Early desmosed islands, like Behemotops, are known from the Oligocene. Pinnipeds appeared near the end of the epoch from an otter-like ancestor. Oceans. The Oligocene sees the beginnings of modern ocean circulation, with tectonic shifts causing the opening and closing of ocean gateways. Cooling of the oceans had already commenced by the Eocene-Oligocene boundary, and they continued to cool as the Oligocene progressed. The formation of permanent Antarctic ice sheets during the early Oligocene and possible glacial activity in the Arctic may have influenced this oceanic cooling, though the extent of this influence is still a matter of some significant dispute. The effects of oceanic gateways on circulation. The opening and closing of ocean gateways. The opening of the Drake Passage. The opening of the Tasmanian Gateway and the closing of the Tethys Seaway, along with the final formation of the Greenland-Iceland Faroes Sill, played vital parts in reshaping oceanic currents during the Oligocene. As the continents shifted to a more modern configuration, so too did ocean circulation. The Drake Passage. The Drake Passage is located between South America and Antarctica. Once the Tasmanian gateway between Australia and Antarctica opened, all that kept Antarctica from being completely isolated by the Southern Ocean was its connection to South America. As the South American continent moved north, the Drake Passage opened and enabled the formation of the Antarctic Circumpolar Current, which would have kept the cold waters of Antarctica circulating around the continent and strengthened the formation of Antarctic bottom water. With the cold water concentrated around Antarctica, sea surface temperatures and, consequently, continental temperatures would have dropped. The onset of Antarctic glaciation occurred during the early Oligocene, and the effect of the Drake Passage opening on this glaciation has been the subject of much research. However, some controversy still exists as to the exact timing of the passage opening, whether it occurred at the start of the Oligocene or nearer the end. Even so, many theories agree that at the Eocene-Oligocene boundary, a yet shallow flow existed between South America and Antarctica, permitting the start of an Antarctic circumpolar current, stemming from the issue of when the opening of the Drake Passage took place. Is the dispute over how great of an influence the opening of the Drake Passage had on the global climate. While early researchers concluded that the advent of the ACC was highly important, perhaps even the trigger for Antarctic glaciation and subsequent global cooling, other studies have suggested that the delta 18O signature is too strong for glaciation to be the main trigger for cooling. Through study of Pacific Ocean sediments, other researchers have shown that the transition from warm Eocene ocean temperatures to cool Oligocene ocean temperatures took only 300,000 years, which strongly implies that feedbacks and factors other than the ACC were integral to the rapid cooling. The late Oligocene opening of the Drake Passage. The latest hypothesized time for the opening of the Drake Passage is during the early Miocene. Despite the shallow flow between South America and Antarctica, there was not enough of a deep water opening to allow for significant flow to create a true Antarctic circumpolar current. If the opening occurred as late as hypothesized, then the Antarctic circumpolar current could not have had much of an effect on early Oligocene cooling, as it would not have existed. The early Oligocene opening of the Drake Passage. The earliest hypothesized time for the opening of the Drake Passage is around 30 Ma. One of the possible issues with this timing was the continental debris cluttering up the seaway between the two plates in question. This debris, along with what is known as the Shackleton Fracture Zone, has been shown in a recent study to be fairly young, only about 8 million years old. The study concludes that the Drake Passage would be free to allow significant deep water flow by around 31 Ma. This would have facilitated an earlier onset of the Antarctic circumpolar current. Currently, an opening of the Drake Passage during the early Oligocene is favored. The opening of the Tasman Gateway. The other major oceanic gateway opening during this time was the Tasman, or Tasmanian, depending on the paper, gateway between Australia and Antarctica. The time frame for this opening is less disputed than the Drake Passage and is largely considered to have occurred around 34 Ma. As the gateway widened, the Antarctic circumpolar current strengthened. The Tethys Seaway closing. The Tethys Seaway was not a gateway, but rather a sea in its own right. Its closing during the Oligocene had significant impact on both ocean circulation and climate. The collisions of the African plate with the European plate and of the Indian subcontinent with the Asian plate cut off the Tethys Seaway that had provided a low-latitude ocean circulation. The closure of Tethys built some new mountains and drew down more carbon dioxide from the atmosphere, contributing to global cooling. Greenland Iceland Faroes. The gradual separation of the clump of continental crust and the deepening of the tectonic sill in the North Atlantic that would become Greenland, Iceland, and the Faroe Islands helped to increase the deep water flow in that area. More information about the evolution of North Atlantic deep water will be given a few sections down. Ocean cooling. Evidence for ocean-wide cooling during the Oligocene exists mostly in isotopic proxies. Patterns of extinction and patterns of species migration can also be studied to gain insight into ocean conditions. For a while, it was thought that the glaciation of Antarctica may have significantly contributed to the cooling of the ocean. However, recent evidence tends to deny this. Deep water. Isotopic evidence suggests that during the early Oligocene, the main source of deep water was the North Pacific and the Southern Ocean. As the Greenland-Iceland Faroe sill deepened and thereby connected the Norwegian Greenland Sea with the Atlantic Ocean, the deep water of the North Atlantic began to come into play as well. Computer models suggest that once this occurred, a more modern in appearance thermohaline circulation started. North Atlantic deep water. Evidence for the early Oligocene onset of chilled North Atlantic deep water lies in the beginnings of sediment drift deposition in the North Atlantic, such as the Feni and Southeast Faroe drifts. South Ocean deep water. The chilling of the South Ocean deep water began in earnest once the Tasmanian Gateway and the Drake Passage opened fully. Regardless of the time at which the opening of the Drake Passage occurred, the effect on the cooling of the Southern Ocean would have been the same. Impact events. Recorded extraterrestrial impacts. Horton impact crater, Nunavut, Canada diameter. Supervolcanic explosions. Ligarita caldera.